Here are two equations for gas density. The first one is D is equal to P times M divided by RT, where P is the pressure, typically in atmospheres or kilopascals. M is the molar mass of the gas. Any unit is fine, although usually grams is what we can most easily pick off the periodic table. T is the temperature in Kelvin, and then R is the universal gas constant. And you'll note here that I've provided two values for R, one for when the pressure is in kilopascals and another one for when the pressure is in atmospheres. So that's why up here where I've said pressure in atmospheres or kilopascals, that pressure unit has to match up with the pressure unit for R. So that enables you to choose the right value of R. Here's another equation for gas density, very similar to the combined gas law. This is what happens to the density of a gas when you change the temperature or change the pressure. This is for when you have the same gas under two sets of conditions, a set of initial conditions and a set of final conditions. And this equation is just kind of fun to say. P1 over T1D1 is equal to P2 over T2D2, which kind of reminds us of Star Wars. Let's do a few problems. Let's find the density of nitrogen dioxide at 75 degrees Celsius and 0.805 atmospheres. Nitrogen dioxide has that formula, NO2, which you should be able to figure out. We notice that there's a Celsius temperature, which is not what we want, so let's convert that into Kelvin right away. So let's go ahead and use this equation where the atmospheres is the pressure from the periodic table. Nitrogen has a molar mass of 14, each oxygen has a molar mass of 16, so 16 times 2 is 32 plus 14, that's 46. Now, in the denominator, which value of R should we pick? We need to pick the one that has atmospheres in it, which is the 0.0826, and then there's our temperature in Kelvin. When we type that in, the numerator is grams, the denominator will be liters. You can check it out for yourself that liters actually ends up in the denominator, 1.29 grams per liter. How about this one? Find the density of argon at STP. We have on the right there argon's little snapshot from the periodic table. Here, we're just going to use the definition of density. Density is the ratio of mass per volume. We need some mass of argon and some volume of argon at STP. What do we know about argon? Well, we know that 1 mole of argon has a mass of 39.948 grams. We know the volume of 1 mole of argon at STP. And the answer is, 22.4 liters. As long as we have a mass and a volume for the same quantity of argon at STP, this ratio will come out just like how we want it. 1.78 grams per liter. Let's do one more. A gas has a density of 0.87 grams per liter at 30 degrees Celsius and 131.2 kilopascals. Find the density at STP. So here you can see that we have a set of initial conditions and a set of final conditions. Let's convert Celsius into Kelvin by adding 273. And when we have a set of initial conditions and a set of final conditions, this might be a good equation to use. Let's go through the problem and see what variables we can fill in here. A gas has a density of 0.87 grams per liter, so that's D1. So that goes in the denominator right there. At that temperature, so that's T1, and at 131.2 kilopascals, so that is P1. Then, on the right side of the equal sign, we need standard temperature, which is 273 Kelvin, and we need standard pressure in kilopascals. And in kilopascals, standard pressure is 101.3. So now we just need to cross multiply and solve that, and we'll be done. But I'm going to go ahead and show you the thinking method again. And here's how the thinking method works. We need a new density, so we set it equal first to the initial density. Then we put a fraction, and we're going to put in this fraction either the 303 Kelvin on top or bottom and the 273 Kelvin in the other place. Let's ask ourselves, right? Let's think. The temperature goes from 303 to 273. That means it cools down. What do gases do when they cool down? Don't they take up less space? And if the same gas takes up less space, doesn't it then have a higher density? And the answer is yes. When the same gas takes up less space, it then has a higher density. Therefore, this fraction has to be a quantity greater than 1. Let's do the same thing for the pressure. The pressure started at 131.2 and ended at 101.3. What must have happened to the volume if the pressure decreased? And the answer is, I think if the pressure decreased, the volume must have gotten bigger. And when the volume gets bigger, what happens to the density? Doesn't it go down? Therefore, this fraction needs to have a value smaller than 1. Either way you do it, you will get 0.75 grams per liter.